All right, well, welcome to week 7. For those of you in Tahoe, welcome to winter. Got cold all of a sudden, gotta love that. But have no fear, I heard in a couple days we'll be back up into the 70s because, it's Tahoe. But anyway, welcome back. Before we continue our discussion of related rates, right? You may remember on Friday we were kind of in the middle of looking at how to tackle these word problems where we've got things that are changing that are related to each other. We're going to do more of that. We're going to definitely do a few more of those to get you hopefully feeling a little bit better about the process. But before we do that, any questions on the homework or anything else? All right, so let's see. We got from 3.9, numbers 10 and 22. 22 getting a couple of votes. We can definitely look at those. Any others? All right, well, then why don't I go ahead and share my screen. We'll go take a peek at those and see what we can do. And if any other ones come up, let me know. I'll be happy to go take a look at those. All right, so hopefully you guys can see my screen that's got the assignments coming, eventually coming. So section 3.9. All right, so exponential and logarithmic functions. So I'm going to guess, without looking at it, the number 2 is one of those where we use the rules of logarithms to help us simplify a differentiation, but we'll find out when we get there, right? It's like Christmas. Can't wait to unwrap this question and see what I get to do. All right, so, number 10 is one of those. All right, so we got f of x equals x cubed times x minus 6 cubed divided by x squared plus 3 to the 7. All right, now this does say use logarithmic differentiation. However, we don't need to, right? We could definitely do this thing just with regular old differentiation, but it would require quotient rule. You see the division, right? So it's going to require quotient rule. Inside the quotient rule, it's going to require product rule on top, x cubed times x minus 6 cubed. And then all of those pieces with the powers are going to require general power rule slash chain rule. So if we were just to dive in as it is, this would require quotient, product, and chain rules, which is fine, right? We know how to deal with those. However, the logarithmic differentiation can definitely make this a little bit faster. So let me go to the whiteboard. And when it says use logarithmic differentiation, what does that mean?
Taking the natural log.
Yeah, we're going to take a log of both sides and then use the rules of logarithms to expand it so that then the derivatives are a lot easier. So let's think about what the rules of log say here. So we're going to get the natural log of y. That's going to equal 3 natural logs of x plus 3 natural logs of x minus 6 minus 7 natural logs of x squared plus 3. So just to refresh your memory on the rules of logs, when there's division, the stuff that's being divided gets subtracted. That's why there's a minus on this one. multiplication, so the things on the top get a plus. And then these 3's and that 7, those were the powers that come out front as multiples. So the rules of logs, let me expand it this way. Boom. All right, now we're ready to differentiate. So we just took a log of both sides. Now we're going to differentiate both sides with respect to x. All right, so for logs, really easy. You always get a fraction. What goes on the bottom of the fraction is what's inside the log, and what goes on top of the fraction is the derivative of what's inside the log. So the natural log of y is going to give us y prime over y. This 3 is a constant multiple. Natural log of x gives us 1 over x. So you write that as 3 over x. All right, the next one, 3 is a constant multiple. We get x minus 6 on the bottom. And we get the derivative of what's inside on top. Well, the derivative of x minus 6 is 1. So that's done. Okay, and then we get minus 7. Again, the x squared plus 3 goes on the bottom. And then on top goes the derivative of what was inside. So the derivative of x squared plus 3 is 2x. All right, well, there's the differentiation. Done. Didn't require any kind of product rule, quotient rule, nothing. It was all super fast. Okay, so before we move on, because we're not done, but before we move on, any questions on this stuff? All right, so then what's the last thing we have to do here?
Multiply the y.
Yep, we need to get rid of that y. We need to multiply by the y, and we'll substitute it back in with all of this garbage. So y prime then is going to be 3 over x plus 3 over x minus 6 minus 14x over x squared plus 3, all of that times y. And there we go. So there's the derivative of y. Now, is it possible to simplify this? Yes. Are we going to do it? No. We're just going to go ahead and leave it like this. But yeah, you could get a common denominator in here and then see if there's stuff that cancels and yada, yada, yada. But we'll just leave it like this.
In general, like for the computer, is it expecting it to be in that format?
I have no idea what the computer expects. The only thing, well, okay, you know what? Let's see. Let's see if the computer likes this as an answer. So let me go ahead and write this thing down, and then we'll put it into the computer, and we'll see if it's smart enough to recognize that that is correct. But yeah, when it comes to questions like that, Ollie, like what the computer expects, since I didn't program it, I have no clue what it actually expects or wants as an answer. So let's go back over there and see what we can do with this guy. All right, so we got parenthesis. Inside that parenthesis, I've got a fraction. Let's see, the first fraction was 3 over x. And then we're going to add to that another fraction that was 3 over x minus 6. And then we're going to subtract from that another fraction, which was 14x over x squared. Oops, x squared plus 3. Okay, and then that was all times another fraction. Nope, that's not what I wanted. Let's try times. There we go, another fraction. So we've got x cubed times x minus 6 cubed divided by x squared plus 3. And all of that was raised to the 7th. Okay, so if I actually copied down what we found along the way correctly, that is it. Okay, well, here we go. Check your answer. Uh-oh, syntax error. Oh, I wonder what that is. Okay, let's try that again. Yay, it liked it. So I guess there's our answer, Alia, that it's fine if we put it in this way.
Thank you.
Yeah, you're welcome. All right, so what other questions do we have about 10 before we move on to 22?
I think I simplified it more, and that's where I got lost.
Okay.
Because I thought I was like, there's no way the answer is this long.
Yeah, and for sure, because then there's more possibility for making mistakes, and adding and subtracting multiple fractions can get kind of messy.
But now that you told us you don't care and we can leave it like this.
Yeah, why not? Right? I mean, that's the derivative. That's the answer, or it's a form of the answer. So. All right, well then let's go look at number 22. So that was the other one that people asked about here. Oh, and if it's the last question, it's got to be hard, right? Oh, well, because it's a word problem. There we go. All right, so we got the population of Toledo, Ohio in the year 2000 was approximately 4,700 people. Assume the population is increasing at a rate of 5% per year. All right, so write the exponential function that relates the total population as a function of t, the number of years since 2000. And then we're going to use part A to determine the rate at which the population is increasing in t years, so p prime. And then we're going to plug in 7. Okay. Let me write down the pertinent information here, and then we'll go to the whiteboard. All right. So how are we going to attack this problem? Ideas, thoughts, suggestions?
A naught equals e to the negative kt.
Okay. I don't like a couple of things about that, but you're definitely on the right track. Let's do this. So we've got P, right? That's our population. I don't want to write that as the fact that you used A is not the problem, Susanna. It's the fact that you said A naught, because A naught would be the starting amount. And so that's what we're going to want here. And then we're going to have e to the kt. The other issue I had, you said a negative kt.
Yeah, that was the equation I remembered.
What if we have a negative there? What does that actually mean?
It's decreasing. Oh wait, no, your problem is increasing. I think I had a problem that was doing the opposite. That's why.
Okay, so yeah, so if we have a negative here, that means that we're decreasing. Our population would be decreasing, which we clearly don't have, right?
Yeah, you're increasing.
Ours is increasing. Okay, so this is the basic formula for exponential growth. So anytime you have any kind of a problem that says, you know, you've got something growing, and like the human population, believe it or not, actually grows faster than exponential, but we'll still go ahead and use that model here. But most creatures out there do grow exponentially, right? But we got a p equals p naught e to the kt. So what are those different things? Well, p naught, this is your initial population. And so if we're talking about, like in this example, a population of, was it Cleveland? Then it's actually the number of people in Cleveland. But it doesn't necessarily, I mean, it could be the number of kokanee in Lake Tahoe. It could be the number of elk in Glacier National Park. It could be, you know, whatever. But it doesn't even have to be animals or creatures. If we're talking about money, this could be the initial amount of money in your bank account. If we were talking about radioactive decay, it would be the initial amount of radioactive isotope, right? So the initial mass or whatever it happens to be. So even though I wrote initial population, just realize that that population could be the initial amount, period. And that's probably where, Susanna, you have that, you think A sub, you know, A naught is probably for amount, right? But regardless, that's going to be our initial. E, of course, is E. And then we've got K and T. T, this is your time. So it'll be the number of time periods or whatever. And then K is either your growth or decay. I'm going to put them together. It's your growth or decay rate. The only difference, as I kind of mentioned before, is that growth is going to be positive and decay is going to be negative. And that's because of how exponential functions work. If you think about exponential functions, they have the same general shape, right? The two basic shapes are either this one or this one. And that's what the change in the sign does. If the k is positive, it's one of these increasing ones. If k is negative, it's one of these decreasing ones. So just a little bit of pre-calc reminder. All right, so far so good. All right, so now we can actually put in the things that we know. All right, we know that in this specific case, we started with an initial population of 470,000. We have a growth rate of 5%. So we're going to put here 0.05. And then t. So this would be assuming exponential growth with this rate. Now, I do want to address something that I saw pop up in the chat. Error is put in here, 1 plus 0.05. And this is another way of actually looking at growth, exponential growth. And that one looks like this, where we have P equals P naught plus 1 plus K over N raised to the NT. And this is the same idea, where K is the growth rate, P naught is your initial population, T is time. But now N would be the number of times that we're actually computing growth per time period, which in this case would be 1 if they say it grows at 5% per year. And so this one would look like P equals 470,000 times 1 plus 0.05 to the t. And I'm guessing that's probably when Erez put in 1 plus 0.05 is what he was getting at. Is that right, Erez? Yeah, okay. All right, so the real question is, which of these do we use, right? Do we go just straight to the exponential growth formula, or do we use this guy? Okay, so this one's a little bit more difficult to kind of see even what the difference is between these, but let me talk about money, because money is sometimes a place where we can see this a little bit better. I don't know if anybody's ever taken out a loan, like a student loan or a car loan or a home loan or something like that. But they'll often give you two different interest rates, right? They'll give you an interest rate and they'll say, oh, the interest rate is 5%. But then they'll also say that there's the APR of whatever, the annual percentage rate. And basically an APR is what number goes up in here in a continuously compounded that equates to the interest rate that we just gave you. And so for this one, since we're being told it grows 5% per year, that 5% per year, we actually do want to use this second guy. So we're going to use this one right here. The 1.05 here, if you think about how this works, if I put in a 1 here, I'm going to get 470,000 times 1.05. That 1 was the original population, and the 0.05 is the 5% increase. When we kick up to t equals 2, well, now we're going to multiply by 1.05 again. So we're going to get that population from the end of the first year plus another 5%. Kick it up to a 3. Well, we get that number plus another 5%, plus another 5%, and so on. So for this one, since they're telling us how much is happening per year, we're going to go ahead and just use this formula right there. So these can be a little bit tricky, for sure. But you're going to end up using one of these two formulas. This first one, this is what we call continuous compounding. And it's more of a theoretical kind of value, but it is how a lot of things are compounded. Like if we're going to talk about, say, inflation rates, stock market increases, and things like that, that pretty much is just always happening, right? It's not like, oh, today we looked at how much inflation happened, and then in a month we calculate inflation again, and in a month we calculate it again, right? It's just sort of a continual deal. And so that's when you use continuous compounding as opposed to this one, which is just, we just call it compounding. But again, n is the number of times per, and I'm going to put here time period, even though it usually is years. So for example, if this was going to be one of those things where we went and we calculated the population every month, then n would be 12. All right. Or if we were going to calculate it every quarter, n would be 4. Every day, 365, and so on. So if we were just going to do it every year, then it would just be once. All right, well, anyway, so we got our formula. We built our formula. Now we're ready to differentiate it. So I'm going to erase this stuff with the continuous compounding since that's not what we're using. So let me just kill this real quick, and this is where we'll go do our derivative. All right, so here's what we got. We got P equals 470,000 times 1.05 to the T. So let's differentiate it, right? We want P prime. So the 470,000 is a constant multiple. But now we need to differentiate 1.05 to the T. So that's A to the T. So what's the derivative of A to the T? Does anyone remember? Okay, so there's going to be a natural log. I'm not going to bother taking a natural log, Aris, because we already did it for every possible one. But it's just that same A to the T times the natural log of A. So that means that this is going to give us a times natural log of 1.05 times 1.05 to the T. So there is the rate of change for the city of Cleveland, I think. And so then the last question was use this to estimate what it'll be in 2007. And so T here was such that 0 was the year 2000. So now P prime of 7 then would just be 470,000 natural logs of 1.05 times 1.05 to the 7th. And the way to interpret this is saying, how is the population changing in 2007? It's going to be this many people per year. All right, so questions on this one? What questions do you have for me here?
So for my problem, it was talking about the half-life of an isotope.
Okay.
And I remember the values. I don't have it pulled up at the moment, but you started with 10 grams and you had a half-life of at 13 hours. Every 13 hours it had a half-life.
Okay.
And I can't remember if there's anything else in there.
Okay. Well, how about, yeah, go ahead.
Would you use that second formula and then would n be like 13 hours?
Okay, so if you're going to do a half-life problem, let me let me address that in just 1 second. But before I go to half-life, any questions about this specific one? Before we kind of change our patches slightly. All right, I'm going to clear all the drawings, so last chance. Okay. So half-life, right? Here's how half-life works. So half-life, this is the amount of time for half of the material to have gone away, to have decayed. Half of the material to decay. All right, so let's give a name to the half-life. I'm going to use T, big T, to be the half-life. And so basically, here's what we know. If we started with, let's go ahead and use the same formula that we did before for exponential growth. Now, for half-life, you are going to use this one, because radioactive decay is a continual process. It's not like it happens and then a minute later it happens again. It's a random kind of thing, so it's continuous. So we're going to use this continuous compounding. But basically how this works is we know that we're down to half of what we had before after that amount of time, right? If I were to plug in big T for my time, my population, my amount of radioactive material or whatever, is half of what it was before. So that's why I just put 1/2 P naught. So with an algebra, I can divide by P naught. So those things are gone, and what I'm left with is 1/2 equals e to the k times big T. I can actually solve this for k. If I take a natural log, get natural log 1/2 is equal to k times big T. So k is going to be the natural log of 1/2 divided by big T. So if you're told the half-life, you can actually use this formula to figure out k. And once you have that, then you know everything, because you'll have your initial amount, right? Like, I forget what number you specifically said, but it was like 20 grams or something like that, right? So you go, okay, well, I'm going to have 20 grams, and then it's going to be e to the whatever this number was. And I think you said your half-life was like 13 hours or something. So you would take natural log of 1/2 divided by 13. And that's going to be your K. And then that's everything you need, because now you'll know exactly how much you're going to have after a certain amount of time. And so then you can use that formula and adjust it for whatever information they give you that you're trying to find. Right? So like if they ask you, how much material do you have after, 24 hours, you would put 24 in for T. If they ask you how long until you only have 1 gram left, well, you put a 1 in over here for your P, and then solve for T. So regardless, once you get this, you get your K, that and your initial amount is enough for you to be able to do anything. So does that make a little more sense for that one?
Yeah, I didn't know what formula I was supposed to use for it. I just kind of gave up and went to bed.
Yep, one of those where you're like, I'll just ask Bruce, he'll tell me tomorrow. So. All right, cool. So yeah, so if you got something with a half-life, you can do that. This also works like if you have like a doubling time or something like that, because sometimes, again, with like money, that will be something that will be asked and say, okay, well, suppose that you start with $1,000 and the balance doubles in 10 years. What's your interest rate? Kind of thing. And so you could do the same thing. It would just be P naught and then like 2 times P naught, or a tripling 3 times P naught, or anything else. So if you ever know the multiple on P naught, that's actually sufficient to find K. All right, coolio. All right, any other questions on this one, or are we about ready to move on? All right, well then I'm gonna go ahead and stop sharing here. And so yeah, don't forget the homework is due tonight by midnight. But hopefully that's progressing along nicely. So what I'm going to do is I'm going to hop up to the whiteboard and we're going to keep working a little bit with related rates. So I will be right back. All right, so last time we were talking related rates, and we saw that related rates, there were problems. Basically, we have to figure out what thing we're trying to find is changing, how, let me start again. We're going to be asked how something is changing, right? We're going to be looking at how quickly is a distance changing, or an angle changing, or a volume changing, or something like that. We're going to have to be able to figure out how that's related to other rates that we're told. So we got to find some sort of equation that relates them, so then we can differentiate implicitly and make the connection. So last time we talked about two different examples. We talked about the bird that was flying towards us and how the angle of observation changed as the bird moved. And then the other one, we were looking at that conical pile of sand, and how as sand was coming off the conveyor belt, we were seeing that the size of the cone changed, right? And so those were a couple of examples. So what I want to do today is share some more. We're just going to do a few more here so that we can get the kind of the process and talk about general strategies. So what I'm going to do is share on my other screen, like I did before, some examples. So this list should look familiar because it's the same one that we saw last time. We're just going to do some different ones of them. So here they come. So you'll probably recognize that first one. That first one was the conical pile of sand. But we're going to try different ones today. All right. So looking down that list, I say we see if we can set up B. All right, just so the second one right there. So what it says is that a boat is pulled by means of a winch on the dock that's 12 feet above the deck of the boat. The winch pulls in rope at a rate of 3 feet per second. Determine the speed of the boat when there's 13 feet of rope out. All right, so as I mentioned before, these are going to be word problems. Good old word problem here. But let's see if we can get this thing set up. So I'm going to give you one more minute here to write that down or take a picture. You can always go back and look at this thing later if you need, right? But okay, so let's see if we can get this thing set up. So I'm going to stop sharing so we can see the whiteboard a little bit better. But let's take all that information and put it in here. So I'm going to start by drawing a picture. So we've got the dock, and we've got water down here, and out in the water is our boat. All right, so we're pulling in on this boat with a winch. So there's something up here, like pulley type thing. That's pulling in our boat. Okay, so here's just the general picture of everything for the scenario. Now, there's a little bit more information that they give us. They tell us that this winch is 12 feet above the deck of the boat. So this right there is 12 feet. And they also told us that at this moment there were 13 feet of rope out. I'm going to leave that for just a second. We're going to come back to that in just a second. But here's basically the picture. The reason I don't want to write 13 here is because this length is going to change, right? As the boat is getting pulled in, that length changes. This 12 does not. Okay, so I'm going to try not to write anything with numbers permanent unless they're permanent numbers. Okay, otherwise we're going to want to allow for variables. All right, so far so good. All right, so let's see if we can figure out what rate of change we're looking for. Okay, because that's super important. So let's go back and look at what the wording says again. So I'll share this one more time. So looking at B there, what rate of change are we looking for? And you can give it to me in words. You could try to give it to me in some sort of an equation-y type thing if you'd like.
When there's 13 feet of rope out, what's the speed?
Okay, so yeah,
so the change in like rope length.
Okay, so it says we want to determine the speed of the boat. All right, so that right there, as soon as you see speed of the boat, and I saw a couple people chiming in on the chat like velocity. Yep, this is a velocity. We know velocity is a rate of change, speed's a rate of change. So that's the rate of change we're looking for. So we're going to try to find the speed of the boat. So I'm just going to write that down. I'll share my whiteboard here again in a second. I just wanted to write it down so we got it. So we're trying to find the speed of the boat. Now, is there a rate of change that we're given? Because hopefully there is, right? There you go. So a couple of people are putting in there. Sarah just said the 3 feet per second. And Bailey is like, that's the change in the rope length. So if you look at that other piece where it says the winch pulls in rope at a rate of 3 feet per second, that's a rate of change. And it's exactly the change in the rope length. So I'm going to write that down here as well. So the rope changes length at 3 feet per second. All right, so this is going to be really important in a related rates question. These two things. One, figure out what rate of change we're looking for. And two, what rates of change are we given? Okay, well, let me stop sharing. So we'll go back to the whiteboard again. So you see, I just wrote down here, we're trying to find the speed of the boat, and we're told that the rope changes length at 3 feet per second. So here's what I'm going to do. I'm going to label the rate of change we know, which was the change in the rope length. And just to give that some sort of a letter here, how about we call that X? Okay, so X is going to be the length of the rope. So like right now they told us it's 13 feet, but it's not always 13 feet. It's going to change, right? It's going to change depending upon where the boat is. When the boat is further out, this rope length is much longer. As it comes in, that rope length gets shorter because we're pulling in with the winch. Okay, but let's just call that X. All right, so that means that this rate of change, the winch pulling in the rope, that's a dx dt. All right, so basically the way I've labeled this is going to give us dx dt. All right, so now I need a quantity that's changing that gives me the speed of the boat. So we already know that that's a distance. What distance is that going to be? Like in my picture, what distance is the distance that gives us speed of the boat? And I'll give you a hint. It's
13 feet of rope?
No, it's not the rope at all. The rope and the change in the rope length, that's all due to the winch.
Is it the bottom of the triangle?
It's exactly the bottom of the triangle. If we think about this distance, we'll call it, say, y. that horizontal distance, that's how the boat is moving, right? The boat's not getting lifted out of the water. It's not getting sucked into the water. It's moving along the water surface. And its speed is, how is that number changing with time? So if I call that y, then the speed of the boat, this is going to be dy dt. So the rate of change we were given was the change in the length of the hypotenuse of this triangle. The rate of change we're looking for is the change of this side of the triangle. So both y and x are changing. As we're pulling it in, they're both changing. How they're going to change, well, they're related to each other. So we need an equation now that involves x and y. So any ideas or thoughts on an equation? Oh, you know what you want to do. You're just nervous to say it.
Take a derivative.
Oh, no, before we do that, we need an equation before we do a derivative. But what equation are we going to use that's going to relate x and y?
Slope.
Oh, good guess. Not quite what I want. If it looks like a triangle.
Oh, SOHCAHTOA.
Triangle.
So trick.
We want to use good old Pythagorean theorem, right? We've got a nice little triangle here. Let's use some trig stuff. And if we're looking at just sides, just begging for the Pythagorean theorem. So what we know is that 12 squared is going to, or sorry, 12 squared plus y squared equals x squared, according to my picture. And if you'll humor me here for a second. I don't know if you guys can even see that. I just made this a sun. The glare is a sun. I thought it was appropriate for sailboat exercise. Anyway, all right, so we've got 12 squared plus y squared equals x squared. That's how those quantities are related. And now that we've got that equation, we can differentiate. Okay, so let's do the derivative. The 12 squared, which is a 144, of course, that is constant. So when we differentiate, it's going to go away. The y squared, I'm differentiating with respect to t, not x. I'm differentiating with respect to t. Why am I differentiating with respect to t?
Because of time.
Because of time. These are rates of change with time. Speeds are rate of change with time. So I want to differentiate with respect to t. So because I'm differentiating with respect to t, I need to use implicit differentiation. So the y squared is going to turn into a 2y times dy dt. We wrote it before as 2y times y prime. When I do implicit differentiation, I like to use the letters just to make sure I know what's my variable, what am I differentiating with respect to, and just so that I'm making sure I'm doing it right. So I'm just going to write that as dy dt. Okay, so the x squared, same story, right? It's going to give me a derivative of 2x, but now times dx dt. So we started with this equation that related the quantities, x and y. And by differentiating, we get an equation that relates their rates of change, hence the name related rates. But now this is enough for me to solve, right? I want to find the speed of the boat, which was dy dt. Let me solve it for dy dt. dy dt, I'm going to divide by 2y, so that's going to give me x over y times dx dt. So if I want to know how the speed of the boat is changing, I need to know how quickly the rope length is changing, and that should make total sense. If we start pulling in that rope faster, my boat is going to speed up. If I slow down how quickly I'm pulling it in, my boat's going to slow down. Totally, makes total sense. It also, though, depends on x and y. And x and y are measures of where we are. But if you think about it, that should also kind of make sense. Because if this boat is really far away, and I start pulling it in, it's not going to move as quickly as when it gets closer. When it gets closer, I'm pulling it in much more rapidly. And so it does change as we start pulling it in. All right, so now we're ready to try to answer our specific question, right? How fast is our boat moving when we're pulling it in at 3 feet per second and the rope length is 13. All right, so now is where that 13 is going to come in. Let's think about the different numbers that we have. So we knew that x was equal to 13 at this point in time. We also are going to need a y equal, so I'll leave a spot there, and we also need a dx dt. But the dx dt we know. What is dx dt? All right, so Bailey just put in a 3, and I was going to, looking at the chat, I was going to tell Erez just to say what I said earlier, because when we were talking about rates of change, he had put in the 3 feet per second, right? Remember the dx dt, that was the change in the rope length, the 3 feet per second. But I want you to notice that what I wrote just there wasn't 3. What I wrote was -3. Ugh, why the negative?
Because it's getting shorter?
Good. It's exactly right, because it's getting shorter. With derivatives, remember how derivatives work in terms of their signs. A positive derivative means that our quantity is getting bigger. A negative derivative means it's getting smaller. So since we're pulling it in, since the rope length is getting shorter, that's why that derivative is -3 feet per second. And that's the difference between speed and velocity, right? Remember, speed and velocity are different things. Velocity tells you direction. Speed is just how quickly it's changing. But this one, we really want to be good about it. dx dt is negative because it's getting shorter. Had it been going the other way, that the rope was being let out, then dx dt would be positive.
Can I ask a quick question about an earlier step?
Absolutely. Which one, Alia?
I was just wondering, just to clarify, when you started getting the derivative at the top there, the 2y times dy dt, are you treating both y and x like you would with y if you're doing implicit differentiation because they're both their own functions? Is that what's going on?
That's exactly what's going on. Yep. X and y are both functions of time. The length of the rope and the distance that the boat is from the dock are both changing with time. I just don't know exactly how. So I'm assuming that they are functions of t. So when I differentiate with respect to t, I have to use the chain rule. And so it is, I'm treating them both the same as what we did with y, which is regular implicit differentiation. Yep.
Great, thank you.
You're welcome. Good question. All right, well, we're almost ready, right? We have one more thing we got to get, which is the y. So how are we going to figure out what y is? Because we weren't told it, right? We weren't told how far away from the dock the boat is. So how are we going to figure out that number? There we go. A couple of you just threw it in there at the same time. Pythagorean theorem. Let's go back to the Pythagorean theorem. We know that 12 squared plus y squared equals x squared. So if you give me an x value, well, I can plug that in to find my y. So I've got 144 plus y squared is equal to 13 squared, right? So 12 squared plus y squared equals 13 squared. That's 144 plus y squared equals 169. Y squared equals 25. Or y equals 5. So at this point, when the rope is 13 feet long, the boat is 5 feet away from the dock. So it's almost in. We're almost done. I don't know if you guys recognize those sets of numbers, the 5, 12, 13, but it's another pretty common right triangle. I'm sure you all know the 3, 4, 5. Right? 5, 12, 13 is another Pythagorean triple. You'll see that a lot. Just a little side note. All right, well, we now have all of our information, so we can now figure out dy dt. So dy dt is going to be x over y times dx dt. So we get minus 39/5. Or if you'd rather, negative 7.8 feet per second. All right, so that's the velocity of the boat at this point. It's negative. And if you think about that, that should make sense, because a negative rate of change means that quantity is getting smaller. Y, the distance from the boat to the dock, is getting smaller. We're pulling it in. So it's negative, but it's negative 39/5 or negative 7.8 feet per second. So the speed of the boat is 7.8 feet per second, but its velocity is negative 7.8. All right, well, there you go. We were able to figure out how fast that boat was traveling because we knew this relationship between its distance away from the dock and the length of rope and the fact that the rope was changing length. All right, so another example of related rates. Before we move to another one, I want to give you a chance to ask me more questions on this, because I have a feeling there's probably another question out there. Okay, so sounds like maybe no more questions on this. So then B, the other thing I want to do is, let's write just a little bit of a process, a recipe, right? What steps do we need to take when we're solving one of these related rate problems? Because there were definitely things that I did, there were steps that I did, that if you go back and you look at other ones, I followed those same steps, because there's a process. I definitely have a process when I do these, and I'm going to recommend this process to you. However, if this process doesn't work for you, that's fine. Develop your own process. But here's basically my steps for one of these problems. Okay, here's what I do. First thing first. I determine what rate of change I'm looking for. So I'm putting here that I'm looking to find. So read the question and determine what rate of change do we need to find. What is it? What is that quantity that we're looking for? Like in this case, it was speed of the boat, right? When it was the pile, the pile of sand, it was the change in the height, right? When it was the bird flying over us, it was the change in the angle, right? But always figure out what is the thing that you're trying to find. Okay. The next thing I do is I determine what rate of change I'm given. And I'm going to put a S on there because sometimes it's more than one rate of change. It might be two things that you're told, but or three or four, but always determine what rate or rates of change are given. So in this case, it was the rate of change in the length of the rope. For the conical pile, it was the rate of change in the volume, how much was coming off. For the bird, it was the speed of the bird, the rate of change in the distance. Okay. So always determine what rate of change you're trying to find, and then also figure out which ones are given. All right. Then, this is the hard part. You need to create an equation. Involving these quantities. So in this case, it was the Pythagorean Theorem, right? That was the equation that involved x and y, those two distances. For the conical pile, it was a volume formula. For the bird flying towards us, it was another trig one, but it involved, I don't remember if it was sine or cosine, but it used one of the trig functions. All right, so this is where all the work's going to be. Not all, the majority of the work is going to be creating this equation. Okay. I'm going to talk a little bit more about that step in a second. So we create the equation. Then once we have that equation, this is where we're going to differentiate both sides. And I'm going to put here using implicit differentiation. And so then once it's differentiated, you plug your numbers in and you go. All right, so to me, for me, this is my general process. I figure out what I need to answer. What's that rate of change? What rate of change do they give me? Make the equation that connects them together, that relates them, so then I can differentiate, do my thing. Okay, so that's how I would characterize my steps. But in here, there are some other things that happen. And these are some other things that I'm going to recommend that you do. For number 3, when you're actually creating that equation, one thing I'm a huge fan of draw a picture. Because a lot of times that picture is going to be what helps you see how to relate them. Like think about this one with the boat. Next thing you know, you're seeing that triangle. You're seeing the rope length, the length that's changing in that height of 12 feet, right? So draw pictures, super, super helpful in lots of situations. All right. Another thing that I do that I'm going to recommend that you do, and this is not really part of any of these steps, but for the afterwards. So another thing I suggest you do is make a list of quantities you need to know. So I'm actually going to put here that you need to plug in. So like, remember when we got here and we solved it for dy dt, that formula had x, y, dx, dt. Make that list. That will help you remember what you need to find. And you can start putting those things in. Some are going to be given to you. Some you might need to calculate using the relationship that we found here in step number 3. But that's another thing that I highly recommend you do after you differentiate and you see what quantities you need to know. Okay, so that's how I would characterize my process, what I'm going to do when I want to try to solve one of these things. So now that we sort of have a game plan, a roadmap, let's try another one. Okay, so I'm going to go ahead and share my screen. We'll go back to that list and we'll pick out one that we want to do. But before I go there, questions on any of my steps or what I mean by any of them? Or are we in general good? And when I say good, I mean good with my steps, not feeling good about these kinds of problems. All right, well, hearing nothing, then let me go ahead and share that screen again with the different problems. And let's see, how about we do letter number D? Okay, so let's jump down to D. So D, it says a light shines from the ground onto a wall 25 feet away. A man that is 6 feet tall walks away from the spotlight at a rate of 2 feet per second. How fast is the height of his shadow decreasing when he's 10 feet away from the light? All right, so let's kind of break this down and let's start with what are we trying to find? What rate of change are we looking for? Change in what?
Shadow.
The shadow height.
Shadow height.
Yep, good, yeah. So we got the, you can just imagine if there's a light being shown onto a wall and somebody walks in between the light and the wall, their shadow is going to be on the wall with a given height, right? And so we're looking for the change in that height. So I'm going to write some stuff on the whiteboard. We'll go back. I'll show you the share the whiteboard in a second. I'm just going to write this down so I've got it. So we're going to try to find the change in the height of the shadow. Okay, So we know what we're looking for. What rate or rates of change are we told? Do you see any rates in there? All right, so Bailey just said the man's speed. That's exactly it. If you look at the second sentence there, it says a man that is 6 feet tall walks away from the spotlight at a rate of 2 feet per second. So the word is right there, rate, right? 2 feet per second. That's the speed of the man. All right. So we know that the speed of the man, and I'm going to go ahead and write this down, is 2 feet per second. So there is the quantity whose rate of change is known, right? The speed of man. Okay, I'm going to stop sharing that for a little bit. We'll come back and we'll get some specific numbers in a minute. But now that we've got what we're looking for and the rate of change we're told, let's see if we can build the equation. And see what happens. So let's go to the whiteboard. I'm going to stop sharing. So I put up here that information, right? The rate of change that we're looking for and the speed. So let's draw a picture. So here's our picture. Here's the ground. Here's the wall. We got the spotlight. And then we've got our person here. So that light is shining, and then because of the person standing in between it and the wall, there is a shadow. So I'll make that little green guy over there. That's the shadow on the wall. All right, so let's put in the quantities. We're trying to find the change in the height of the shadow. So I'm going to go ahead and just call that, say, y. All right, so y is the height of the shadow, which means that rate of change we're looking for is dy dt. All right, we also know the speed of the man. So do you remember how it said that he was walking? It's okay if you don't. It said that the man was walking away from the light. Okay, yeah, thanks, Aris. He was moving away from the light. So the distance between the man and the light, let's call that, say, x, right? Because if he's walking away, x is changing. And that's the speed of the man. So those two quantities, x, the distance between the light and the guy, and then y, the height of the shadow, those are the quantities that we want to relate.
Could x also have been the distance between the man and the wall?
Sure. We could have called that x, yep. You want to call that one x? I don't really care.
No, that's fine, just checking.
Because that would be equivalent, right? Like if we were to have, let me just erase this and put x on the other side here. So if we said that this was x, is x still changing? Totally. Is it changing at the same rate as the x I had drawn? Yeah. The only difference would have been their signs. Because what would dx dt be now with the x that Aaliyah just suggested? Would that one be positive or negative? Yeah, good there. So that one's going to be negative because it's getting smaller. If we had done the x as the distance between him and the light, then dx dt would be positive because that distance is getting bigger. So either one of those is fine to call x and use dx dt to measure it. It's just one's going to be plus or minus. So I'm going to go and leave it like this. I'll let you guys drive. So we'll use that x instead of my x. It doesn't matter. It's still going to work out. All right. So far so good. At least in terms of the first couple of steps, figuring out what it is we're trying to find and what we're told. Yeah, okay, I'm seeing some thumbs up. Cool. So now the fun part, now we need to relate x and y.
Pythagorean theorem again.
Okay, so Suzanne says, let's use Pythagorean theorem. Now, why are you thinking Pythagorean theorem?
Because it looks like a triangle.
Okay, you see a triangle. Obviously, we don't quite have a triangle, but we can easily throw on a third side. Let me throw on that third side. And this is probably, I'm going to guess, that's the third side of the triangle you wanted to draw on.
Yeah.
Yeah.
But then we also need the angle theta then.
Okay, so if we knew the angle, we actually don't need the angle to use the Pythagorean theorem because Pythagorean theorem only uses all three sides. But there is a bit of an issue with the Pythagorean theorem, so we don't know all three sides. Right? In fact, we don't know any of the sides. So this is one where Pythagorean theorem isn't what we want to use. Let me help you out. There is another length that I know. What other length do we know here? Good. Errors just put in the chat box. The height, right? We know the height of the person. And then Mariol also put in the, we know a distance away, right? Let's go back to what the question actually told us. May not remember everything about it, so let me just pull it up again.
10 feet away from the light. Oh no,
right.
That's what we're looking for. Never mind.
So it says, the light shines from the ground onto a wall 25 feet away. So there's a distance that we know. We know that this distance all the way across is 25 feet. How about that? Is that going to change? Is that distance going to change? So yeah, that's a pretty easy no, right? The light is fixed, the wall is fixed. That's just 25 feet. Okay, we're also told that the man is 6 feet tall. So this distance right here is 6 feet. All right, so how about that? Is that length going to change? All right, again, no. Assuming he's not stumbling or, anything like that. But if he's just standing up and walking, that should stay the same. And then read a little bit further. It says, how fast is the height of his shadow decreasing when he's 10 feet away from the light? Okay, so that 10 feet, is that going to be changing? Is the distance between him and the light changing? All right, thanks, Ollie. Yes, that is changing. He's walking away from it. So that one I don't want to use as a number. If I'm going to include that, I need to include that as a variable because it's changing. Okay, well, there's some more information. Let's stop sharing again. Let's look at our picture. Because now, I don't know, maybe you're starting to see what we can do, but we can set up a similar triangle equation. Yeah, so Fenrir, you just put in there that the sign is the same, so we can use that to find y. That's the same idea I'm going to use, which was similar triangles. Basically, if you look at triangles that are similar, meaning their angles are the same, and that's what we've got. We've got a smaller triangle. Let me redraw the picture down here that's less cluttered. Right, we've got this smaller triangle and we've got this bigger triangle, and they are similar, which means the ratios of their sides are going to be the same. So that was 6, this was y, this was 25. I'll call this one x. So here's what we can do if we want to set up similar triangle. The heights, the ratio of their heights are going to be the same as, say, the ratio of this length on the bottom. So the heights, we have y and 6. So the y was the big height, 6 was the small height. We can do the same thing with the ratios of their lengths, the lengths of the base. For the big one, it was 25. For the small one, well, that's that length. What's that length? Okay, so it is 10 at this moment, but remember, we want it to be able to change. So I don't want to use a 10. But Aries just put in, how about 25 minus x? If I told you the length from the distance from the man to the wall, you could find this other one by subtracting it. So this is going to be 25 minus x. So again, I don't want to use 10 because 10 is just a temporary length. It's a length at that moment, but it's going to be changing. But there now is a relationship between x and y. All right, that was the hard part, was getting this equation. All right, but similar triangles, this is a really common way to do this. And I just want to go back to what Fenry said when he said sine of, right? Yeah, this angle, we know that its trig functions are going to be the same for the smaller triangle or the bigger triangle. So you could use any of them. You use sine, cosine, tangent, like any of the 6, and use their respective sides. And then you can equate them and you would get something that looks like this. So that's a great way of approaching it too. All right, well, now you can probably see, Alia, why I wanted my x to be the distance away from the light. Because then the way that I would have set mine up, this just would have been an x instead of a 25 minus x. But it doesn't really matter. In terms of the derivative, it's a minor change anyway. All right, well, now that we have that equation, we're ready to differentiate. So let's do a ddt on each side. All right, so y over 6. Well, the over 6, the 1/6, that's a constant multiple. We're going to get 1/6 times dy dt. The other side, the 25 is a constant multiple. And in fact, let me rewrite this side as 25 times 25x to the minus 1. I think it'll be a little bit easier. We don't have to do quotient rule or anything like that. So we're going to do the chain rule. So it's going to be times -1 times 25 minus x to the -2. And then times the derivative of what's inside, which is a negative dx dt. So before we move on, let me just kind of walk through this again. The first 25 is the constant multiple. The minus 25 minus x to the -2 is just the general power rule on this, right? The exponent comes out front as a multiple, decrease it by 1. And then we had to do the chain rule, which is differentiating 25 minus x. 25 is a constant being added, so it goes away. The minus x gave us the minus dx dt. So let me rewrite this because we're looking for dy dt. I'm going to multiply by 6. 6 times 25 is 150. We're going to get over 25 minus x quantity squared. That was that -2. The negatives cancel each other out. And we're left with dx dt. So with the algebra, here's where we are. Okay, so now we're ready to start plugging things in. So let's make a list of the things we need. So we need to know x, and we also need to know dx dt. So I left our picture just so that we could see what the things are. All right, so x and dx dt. So dx dt, that is the speed of the man. And if I recall, was that 2 feet per second? At least that's what we're going to go with. So 2 feet per second. But again, remember that this x needs to be negative. Because if we're going to say that x is the distance between the man and the wall, that distance is getting smaller because he's walking away from the light, which means he's walking towards the wall. All right, so then what's x? What number are we going to put in for that? All right, so Era's just put in 10. Uh-oh, Bailey just put in 15. Ooh, fight. They obviously both can't be right. Okay, so Mariola just said 25 minus x. Well, let's remember, what is the 10? The 10 was the distance between the guy and the light, which in our picture would be this blue. Well, that's 10. If he's 10 feet from the light, that means he's 15 feet from the wall. So with this x, the way that we've set it up, we're going to let x equal 15. All right, so let's see what that does for us then. So dy dt is going to be 150 over 25 minus 15 squared times -2. So that's -300 over 100, or -3 feet per second. So what we're finding is that as he's walking away, the shadow is decreasing in height. And it's decreasing at a rate of 3 feet per second. So it's getting short. But there you go. We just found that rate of change. And we found it because we knew how it was related to the other rate of change, basically using a similar triangle. All right, so that's how that one played out. Before we call it a day, I want to show you that had we gone with my original x, we would have gotten exactly the same thing. So I want you to see that it still plays out, that it didn't really matter which one we chose as long as we did it, as long as we were consistent. So let me erase this piece and let's set it up using my x. So my picture would have looked like this. So if I had done the similar triangle stuff, I would have gotten the y over 25. So the big height versus the, well, let me do the same way, height to height. So big height to short height was y over 6. Big length to small length would have been 25 over x. So it looks a little bit different. Still very similar, but it's a little bit different. If we had differentiated with respect to t, the left-hand side would have been the same as before, so it would have been 1/6 times dy dt. The other side would have given us 25 times minus 1 over x squared. So this would have given us dy dt equals minus 150 over x squared. Oh, sorry, times dx dt. Forgot the most important part. So the derivative looks a little bit different because it's structured a little bit differently. But now for hours, the numbers we would have plugged in Again, we need x and dx dt. But this time, x is going to equal 10. Because x was our distance away from the light, which they told us was 10 feet. And also dx dt now would have been a positive 2 feet per second, because that x is getting bigger. He's walking away at 2 feet per second. So if you were to put those numbers in, we get minus 150 over 10 squared times a positive 2, which still ends up being minus 3. So we would have gotten exactly the same number. We just would have had a different equation. So when we differentiated, we got something different. And the values we plugged in would have been altered because it's not the same x anymore. It's a different x. So good news is that you can do it in more than one way and it can still work out. Either way, what we've just found out is that as this guy's walking away from the light, the shadow is decreasing. The height of the shadow is getting short. It's getting shorter. Next time you're out somewhere where you can see your shadow from a light on the ground, experiment, and you'll see that your shadow actually gets shorter as you move further away from the light. There you go. All right, so these are related rates. And like we could literally do these all day long and still not do all possible related rates questions because there are an infinite number of them. All right, but the process is still always the same. So think about what I suggest. 1, figure out what rate of change you need to determine. 2, figure out what rates of change you're given. Then 3, the biggie, find the equation that relates those quantities. Here was yet another example of some way that we could relate them, similar triangles. So look for Pythagorean Theorem, similar triangles, other kind of like volume area kind of things. Lord knows what they're going to be. It could be like dirt formula, distance equals rate times time. I mean, there are literally an infinite number of ways that you can combine them. But once you've got that equation, then differentiate using implicit differentiation, and then plug in all your values and go. But one thing I definitely want to remind you about, I kind of hinted at it along the way, is when you're talking about numbers, and they give you lots of numbers, like in this one, remember they gave us the length, the distance between the guy and the light and all that. When you're setting up your equation, think about every one of those quantities as, is this quantity fixed or does this quantity change? If it's fixed, use that number. The distance to the wall, the height of the man, those are set numbers. For things that changed, the distance between the guy and the light, the height of the shadow, right? The things that change, make sure you leave them as variables until the end. Like we used the fact that he was 10 feet away from the light, but not until the very end, right? That was like one of the last things we did was using that. So always think about quantities that they tell you. Are they fixed quantities or do they change? Because if they're fixed, put them in as numbers. If they change, put them in as variables. Okay. All right, well, with that, we are out of time. So just want to remind you that there is a set of homeworks that are due tonight. This stuff, related rates, is not part of it, right? So don't worry about that. But what we're going to do on Wednesday is move away from related rates. Obviously, I'll answer any questions if people still have them, but we'll just start looking at more applications of the derivatives. All right. So with that, we will call it a day. Have an awesome couple days, and I'll see you Wednesday.